Welcome back to Professor Gracie's Intermediate Algebra course. Today we are covering section 8.4 from Blitzer's Introductory and Intermediate Algebra for College Students text, and this section covers composite and inverse functions. So first of all, we'll learn what the heck a composite function is and learn how to verify and find inverse functions. And there's a great little test called the horizontal line test, which determines if a function does indeed have an inverse. And then if it passes the horizontal line test, it ends up being a one-to-one function. And then you can use that graph to graph the inverse. So why don't you guys go ahead and pause the movie and do the warm-up, which is to find the domain and range of the given function. Good luck. Okay, let's see how you did. Notice that the domain values of this is just a set of four ordered pairs. The domain values will be the x coordinates of each of these, and the range values will be the function values or output values or y values. So domain is the set we highlighted in blue, which is -1, 0, 1, and 2. And the range is the set highlighted in yellow, which is 0, 1, 2, and 3. Oh, kind of a crazy looking set bracket there. There we go. Much more better. So again, these are the yellow values that we used for the range, and these are the input values used for the domain. How'd you do? Awesome. Okay. The composition of functions. The composition of the function f with g is denoted by f composite g. So that little symbol there is read as composite and is defined by this equation. So this is just one of those things that you need to stick in your brain. F composite g at x is equivalent to f evaluated at g of x. So instead of evaluating a function at a constant like -1 or 5, you might be evaluating a function at a line or a parabola, something like that. The domain of the composite function f composite g is the set of all x such that x is in the domain of g of x. I'll just say g of g. And g at x, so the output of g is in the domain of f, because that's what you're putting into the function f. Okay? All right. So our first example gives us two functions, f and g, one of which, so function f is it's a parabola because it has that x squared, and function g is a line. Very good, a linear function because x is to the 1 power. So our job is to find f composite g at x and then to turn it around and find g composite f at x and see what we get. So here we go. Recall that f composite g at x is f evaluated at g at x. So here, let's go ahead and highlight these functions. Let's let g be, whoops, sorry, my bad. Let's let g of x be in the blue. and f of x will be green. Okay. So here we are. F composite g at x will be f evaluated at g at x, but g at x is the blue, which is 6x minus 1. So let me make sure you can see those clearly enough. I think I'll go here and do this in the blue. So the blue is g at x. So then f composite, well, that looks pretty big. F composite g at x will be, now the function f is the opposite of x squared, but we're putting all this line into where x is. So wherever you see an x, you're going to be putting in 6x minus 1. And then we add 8 to the result. Okay. So, just so you can see, that's where the x was in function f. All right, so now, working that out, we have f composite g at x is the opposite of, so when I square the binomial, I'll get 36x squared, and then I double the product of the ends, so I'll get minus 12x's from 2 times 6x times 1, and then plus 1, and then plus 8. So f composite g at x will be negative 36x squared plus 12x's minus 1 plus 8, and f composite g at x will be negative 36x squared plus 12x's plus 7, and we're done. Okay, so next up, let's see what we get when we do g composite f at x. All right, so we'll have f at x will be in the green. So now we will have g evaluated at f at x. So g composite f at x will be g evaluated at negative x squared plus 8, because that is what the function f is. So let's go ahead and highlight those. Alrighty, so we'll have g composite f at x will be, so remember the x here is in that line. So what we'll have is 6 times all this stuff and then minus 1. So again, wherever we saw an x, we put in that negative x squared plus 8, whereas in this guy, wherever we saw the x, we put in function g. All right, so we have g composite f at x is negative 6x squared plus 48 minus 1. And g composite f at x will be negative 6x squared plus 47. And we're all done. So notice that they end up being quite different. So you just need to recognize that, you know, there's no commutativity going on with compositions. Not always. Okay. Okay. So moving right along, we'll now go into the definition of the inverse of a function, which uses composition. And it turns out that if some function f evaluated at g of x is equal to x for all x in the domain of g, And if g evaluated at f of x is equal to x for every x in the domain of f, then it turns out the function g is the inverse of the function f and is denoted by f inverse. So this does not mean 1 over f. It's actually read f inverse. So when you see a script letter like that, and it's usually an f, then that's read f inverse. Thus, if you evaluate the function f at f inverse at x, you get x. And conversely, if you evaluate f inverse at f at x, you'll also get x. The domain of f is equal to the range of f inverse, and vice versa. Okay, so here's the second example, and our job is to show that each of these functions is the inverse of the other. So what you need to show in this case is that when you evaluate the composition either direction, you'll get x. So let's first do f composite g at x, and if they are indeed inverses, you'll get an x as a result. So remember that f composite g at x is f evaluated at g of x, and we want to know if that equals x. So g of x is x minus 9 over 4. And then plugging that in to f of x, it'll be 4 times all that stuff, and then plus 9, because that's our function f evaluated at g of x. And we want to know, is that equal to x? So just to let you know what all we did here. So g of x is x minus 9 over 4. We're plugging that into the function f. And the x is right here. So that's what we did. And then simplifying, notice that the 4's divide out. So let's look what we'll have. We'll have x minus 9 plus 9. We want to know, is that equal to x? Well, negative 9 plus 9 is 0. So x equals x, so that one checks out. Now our next job is to check that g composite f at x, is that equal to x? Well, g evaluated at f at x, want to know if that's equal to x. Well, f of x is 4x plus 9, so we'd be evaluating g at 4x plus 9. Again, we'll do f in the green. So let's see what we have. And this is the x for the g. So we will have 4x plus 9 minus 9 divided by 4. Is that equal to x? So this is what we did with the 4x plus 9. This is the x portion of g. So we'll get 4x plus 9 minus 9 divided by 4. Is that equal to x? 4x plus 9 minus 9 divided by 4 gives us 4x divided by 4. We want to know, is that equal to x? So the 4's divide out, and we'll get x equals to x, so that checks out. Okay. And let's make sure that we've answered everything. So because we verified that f composite g and g composite f at x both equal to x, we verified that these functions are inverses of each other. All right. So now there's certain steps to finding the inverse, right? So what you do is you replace f of x with y in the equation for f of x. So we want to write it in equation notation. Then we interchange x and y. So this is just a trick. It's steps because of the fact that inverse functions reflect across the line y equals x. We swap the x's and y, and we see if we can solve for y after swapping. If we can't isolate y, meaning if this equation does not define y as a function of x, which means we can't isolate x, then the function f, and then sorry we missed an s here, does not have an inverse function, and this procedure would end. If you are successfully able to isolate y, meaning that it defines y as a function of x, the function f does have an inverse function. Now, the last step, it's very important. If f has an inverse function, you must replace the y from step 3 with f inverse at x. Otherwise, you just kind of made up your own math. It was we did that as a procedure, but we've got to replace that y with f inverse because what you found was the inverse. And then if necessary, we can verify a result showing that f at f inverse at x equals x, and that f inverse evaluated at f of x is equal to x. So you can always check your work. Okay, so next up, oops. We are looking to find an equation for f inverse at x, the inverse function. So we'll use those steps. So step 1, rewrite f of x as y. Step 2, switch the x's and the y's. And now step 3, we want to solve for y, so we want to isolate y. So if we multiply both sides by 1/4, we will get, these 4's will divide out, and you see we'll get x over 4 is equal to y, which of course by the reflexive property means that y is x over 4. So the fourth step, f inverse at x, we're changing y to f inverse at x, is equal to x over 4. And that's the answer. All right, so for part B, again, step 1, y equals 2x minus 3 over x plus 1. Second step, change the x's and y's. So x is equal to 2y minus 3 over y plus 1. And I'll move this over. And then we will have, if we multiply both, whoops, we'll do another line for solve. Okay, so here we go. We're in the process of solving for y. So we'll get xy plus x is equal to 2y minus 3. We need the y's on the same side so that we will be able to factor them out. So if we subtract 2y from both sides and then x from both sides, we'll get xy minus 2y equals negative x minus 3. Factoring out a y, we get this. So then, dividing both sides by x minus 2, these guys will divide out, and we will get y equals negative x minus 3 over x minus 2. And then that fourth step, we need to rewrite y as f inverse at x. You know what? Let's write it down here so we have more room. So the fourth step, f inverse at x is equal to negative x minus 3 over x minus 2. And we're done. So both of those worked out just fine. Okay, so next step, the horizontal line test for inverse functions. A function f has an inverse that is a function called f inverse if there is no horizontal line that intersects the graph of the function f at more than one point. All right. So here, notice that if I draw, there's many places I can draw a horizontal line, and I cross at more than one point. Do you see this? So therefore, this one fails. This one, we're good, right? You can pick anywhere on this line and it passes the horizontal line test because it doesn't hit more than one point. Just one point is where it's hitting with each horizontal line you attempt. And this guy, I mean, it starts to look like it won't pass, but believe it or not, this here is called a horizontal asymptote. So it's going to get closer and closer and closer to 0, but it'll never touch. So this one also passes. So what we found out was that graphs B and C have inverse functions because they pass have inverse functions because they pass the horizontal line test. Okay. Graphs of a function and its inverse function. So there is a relationship between the graph of a one-to-one function f and its inverse f inverse. Because inverse functions have ordered pairs with the coordinates reversed, if the point AB is on the graph of f, the point BA has to be on the graph of f inverse. The points A, B, and BA are symmetric with respect to the line y equals x. Therefore, the graph of f inverse is a reflection of the graph of f about the line y equals x. So in this last example, it's asking us to use the graph of f to draw the graph of the inverse. And what we got to remember is that the graph of the inverse is going to reflect across the line y equals x, which is the one that I'm dashing in right now. Okay. So what one can do is you can look at ordered pairs on the graph. So if you take a look, 0, 0 is going to be the same point. So if we go f, points on f, let's write that out. All right, so points on f and points on f inverse. Okay, so 0, 0 is on F, so therefore 0, 0, if you switch them, is going to still be 0, 0. That's on F inverse. So now what about 2? Do you see that 2, 8 is on the graph of F? So what's going to be on F inverse? Good. 8, 2. You just swap them. So 8, 2 will be on F inverse. And look at that. If you folded across that line, that red line, do you see they would fold on top of each other? That's what they mean by symmetry. Also, negative 2, negative 8 is on a point on the graph of F. So negative 8, negative 2 will be on the graph of F inverse. And then here's some other ones that don't have a big change. 1, 1, you know, when you flip them, you get the same result. Do you see? And then negative 1, negative 1. Again, when you switch them, you get the same result. So here, I'll go ahead and in green, I probably should have done them in green. So these are the graphs for F inverse. So the graph will look something like this. And we did that solely using the original graph. Kind of cool, huh? So we'll do our arrows at the end. And by the way, there were implied arrows at the end of this guy that the graphing calculator just doesn't make. Alrighty, well that wraps up the lesson for today. I hope you have a wonderful day, and don't forget to do at least some of the problems from the 8.4 problem set. Bye.